This is a production of Cornell University.
All right, here's that distribution, okay? And here's that equation, okay? The soil forming factors is a conceptual model. The function of the combined effects of these factors, climate, organisms, parent material, relief, topography, is going to create, acting upon this parent material, is basically going to create a soil. And it's going to control that distribution. Now, one little fly in the ointment. Do these things stay constant? No. Which means if they don't stay constant, this is not going to stay constant. Soil is what you see today. You come back tomorrow, that material that you're looking at may or may not be the same thing. Does that make sense? Okay. So let's start. Parent material. Okay? Parent material is basically the thing upon which the soil is made. Okay? It's organic material as well as mineral deposits. These mineral deposits are derived from chemical or physical weathering of basically rocks. Okay? This is a map. This is actually out of your book. And I don't even know what all the numbers mean. But this is basically a map of all the regolith, the hard rock, bedrock distribution of the United States. Different bedrock materials across this, or in some cases not bedrock, but parent materials. So here, number 7, this one I actually do know, is the coastal plain. Okay? That coastal plain is the product of the Appalachians and these Piedmonts. Okay? But it is not the same material. Okay? It could be mineralogically the identical thing, but it could be a smaller particle because it's weathered away physically. Or it physically or chemically could be something very different because of chemical weathering. Okay? It's been transported from this, and it has also been interacted by the ocean. Okay? So I have a different parent material here than here, even though this parent material, in all likelihood, was sourced from here. Make sense? Okay. So our first controlling factor is the distribution of the parent material. Where it is, and how it's been put there, and how it's been processed to be put in that place. There are lots of different types. There are direct effects of this parent material on the soil. These are inherited effects, i.e. if I have a granitic type of material, I'm going to have a sandy parent material. It's going to be sandy. On the other hand, if I have a shaly material, like we have around here, I'm all likelihood I'm going to get an acidic type of parent material. I've inherited that from the soils have inherited that from the parent material. We also have indirect effects or acquired effects. These effects are produced due to the weathering or the processing of that parent material. Okay, I can start, let's go back to the granite example. I start with a very large boulder, and as it weathers, it's going to start turning into sandier material. It's still granitic, but it's now sand, so the size has changed. The size of that material has changed. Okay? Now, there are a number of different types of rocks, and we'll talk about these later in the semester. But we're basically looking at hard rock type of material, whether it's sedimentary, igneous, or metamorphic. We're also talking, when we're talking about mineral material, we're also talking about unconsolidated material. Unconsolidated material is stuff that's not sticking together, in essence. These are the gravels, the sands, the drift materials. Okay? I've introduced this idea of texture, and I don't want you to confuse texture with the soil itself. Texture is a measurement of the soil. Okay? It can be a feature of that soil. Yeah, okay, I have a sandy soil, but that sand is not necessarily a product of that soil. That sand could have actually been transported for someplace else, been deposited here, and has become a parent material. Does that make sense? Okay. And we also have secondary minerals. Materials that are not these primary minerals that basically came from either the volcanic ejecta or have been consolidated, but basically have been processed on the surface of the planet and become another mineral through chemical and sometimes physical weathering. Okay? It started as one type of mineral, and through processes at the Earth's surface have been modified into a different type of mineral. we call these secondary minerals. These are all potential parent materials. Okay, this is the material from which that soil is born. Questions? Go.
So you were saying how the granite, like, it gets broken down and then it becomes sand. So
Right.
I remember talking about sand, silt, and clay. Like, can sand become clay?
Sand ultimately will become clay, but it's a long, long process. The sand is basically silica oxide. It's extremely resistant to both physical and chemical weathering. That doesn't mean, I guess go back to my give me a weak acid in a million years, that doesn't mean I can't weather it away. But some minerals are more weatherable than other, both physically and chemically. Okay? And so if I start with a sand versus a shale, start with the same size rock and I put it into acid, the shale is going to weather quicker. If I take the sand and the shale and I put it into a tumbler, the shale is going to weather quickly, faster than the sand or the granite. Now, when I put it into a tumbler, I'm not actually changing the shale chemically. I'm just changing its size. And it's the same thing that's happening to the granite. On the other hand, if I throw it into acid, I'm potentially not just changing its size, but I'm also changing its chemical nature. And that's what we start talking when we talk about physical versus chemical weathering. Physical weathering does not change the material that it's weathering except for size. Does that make sense? I mean, I'm basically taking a rock and I'm cutting it in half. I got two smaller pieces of the same thing. On the other hand, if I take a rock and I put it into acid, I'm dissolving certain things preferentially over other things out of that rock. So that rock is literally changing into something else. Does that make sense? Yes? No? Kind of-ish? All right. Does that make sense? Yeah? Okay, we got this? Now, if we look at this, so we're going to basically put this out in a flowchart. And this is straight out of your book as well. But if we look at the rocks, now we also have plants up here, and I'll talk about those in a moment. But if we look at these rocks and minerals of the parent materials, you basically can have a number of scenarios. First scenario, my soil is going to form in situ, in place, from those rocks and minerals that are right there. Okay? And there, what we call that as a residual soil. Okay? The parent material basically becomes the soil in place. Now, certainly with weathering, the surface processes of the planet, there's a lot of dynamics going on. We have wind, we have water, we have ice, okay, we have gravity. These things can move that parent material from one place, either through weathering or physically moving something, to another place. Okay? So if we have this rock and mineral material transported by water, it can be transported and deposited into lakes or streams or even into the ocean. And we have certain names for these terms. Has anybody heard the term lacustrine before? It basically means lake-laid material. Okay, so if I have this water moving into a lake, I have a lacustrine parent material. That parent material initiated someplace else. It's not lake parent material, it's lake-laid parent material. Water transported into a lake. And we can have the same thing happening with streams where it becomes alluvial, or going into an ocean where it becomes marine. If the transportation happens to be gravity, it becomes a colluvial material. And you can imagine as we move through these, okay, here's ice transportation where it's deposited by ice and it becomes till or a moraine. Or it's been ice transported and then moved by water where it becomes outwash, lacustrine, alluvial, and marine. So it goes right back to these. Or it could be wind transported and it becomes aeolian. Okay, these are the processes of moving that parent material. Okay, it is not the parent material itself. It's the process of moving it. Now, the interesting thing about this process of moving is the process of moving will potentially modify that parent material. And it will also lay it in a pattern or in a way that will affect how it is in turn weathered. Okay, the people that have been out in the field already will understand this story. Okay, but if I have a material that's being laid by a stream, and it's a stream that's around here, and we have a spring thaw, okay? Some springs are really warm, and we have a fast thaw, which means we have the streams that are just pouring out water, a lot of energy, okay? And some springs are not so warm, and the energy of the water coming out of those streams is a lot less. Now, if my material is being transported by water into an alluvial fan, a stream delta, the effect of that energy is going to lay different sized particles on the stream bed. Does that make sense? So the bigger things are going to be deposited at this one location on heavy stream flow. The same spot on a season that is a cooler season and I have less water flow, this same spot is going to have smaller particles being deposited because the high energy is upstream. Okay? You have to have high energy to carry big things. And if I don't have high energy, the big stuff is going to be dropped off earlier. Okay? So all of a sudden, I have a stream delta that has a variety of different strata in it. Okay? Now, if that strata, that variety of different strata, is going to become a soil, one can certainly imagine that the finer particles are going to be weathered at a different rate than the coarser particles. Why? Go back to our story about volume. Okay? I have a given volume. Remember that cube that I had? And I start cutting that cube up, same volume, but the finer texture is in that cube, the more surface area I have. The more surface area I have, the more interactions with the environment. The more interactions with the environment, the faster the weathering. Does that make sense? All back to the transport of the initial parent material into a new arrangement affecting how the soil is made. Cool? Questions? Good? It's just this too early or I'm that good? No, obviously not. Go.
So the names there, those would refer to like the whole like section of soil because of like how it's deposited and everything, or is it like the texture?
It's the nature of the deposit. This refers to the deposit. Okay. This lacustrine could be a lot of different types of parent material, but it's how that material has been deposited and it's sort of its arrangement in space. If it's a lacustrine deposit versus a till deposit, in our minds, we have, okay, I know how till gets transported there, and I know how lake. So I would see if I have a lacustrine, I'm going to have thin strata stuff coating. If it's a till, it's just going to be this big, huge pile of stuff.
Okay.
Does that make sense?
Yeah.
Okay. We cool so far? We good? Questions? All right, so let's move on to the next one. Climate. When we're talking about climate, for all practical purposes, we're really talking about moisture and temperature. Okay? Now with climate, we're also talking about how that climate's moving and in the interaction of it. But for all practical purposes, we're basically talking about water and temperature, or precipitation and temperature. Okay? How that water is being delivered, how much of it, how long, or how is the incidental arrival of that material, of the water. Okay, climate, how warm is it? How long is it warm? What's the cycle of warmth and cool? Okay, water happens to be the main agent of weathering. I mean, you think about it. Any kind of chemical reaction, not any, most chemical reactions really require water to basically be there. Okay, so if I have water in a system, I'm going to be encouraging chemical reactions. Okay, I have that water in the system. What's going to happen when I have a warm temperature versus a cold temperature? What's the rate of reaction going to happen? What's going to happen to the rate of reaction? Has anybody ever heard of the C10 rule? Okay, for every 10 degrees Celsius, the temperature increases. Reaction rates increase by 2. Okay, so I start on the tundra. And I've got water. It's a spring day, so let's say it's just 1 degree Celsius. It's just above freezing. Okay, so I have water. Now I start moving from that tundra all the way down to the tropics. Okay, where suddenly I'm in 20 and 30 degrees Celsius temperatures. Okay, so I've started at 1 and I'm now at 30. Chemical reactions have increased times 2, times 2, times 2. What is that going to mean to the rate of weathering? It's going to be dramatically increased. All right, so that's why temperature and precipitation together really drive those reactions. Now, part of this also has to do with the seasonality of it. Just because it's hot doesn't necessarily mean there's water. Just because there's water doesn't necessarily mean it's hot. Okay? It's the combination of these that are going to produce this drive. Okay. 3 major controls by climate. First control is organic matter accumulation. Okay. Anybody have off the top of their head, where am I going to think? If you think of organic matter accumulation, what type of scenario are you imagining? If I'm going to start seeing an accumulation of, imagine a wetland. If I'm going to start seeing an accumulation of organic matter, what's the scenario, climatic-wise, that's going to produce that?
Low temperatures.
Low temperatures, that's a good one. Why is low temperatures going to produce organic matter? It's certainly going to slow down primary production. But what else is it going to slow down? It's going to slow down decomposition. Okay? So one would think, well, damn, if I'm in the tropics, I'm going to get lots and lots of organic matter. That's where I'm going to see the accumulation, because I'm going to get lots and lots of primary production. But if I'm in the tropics, I'm also going to run into the C10 rule. Decomposition rates are also going to be accelerated. Okay, so why would I find accumulation of organic matter in the tundra? Well, plant growth is really, really slow, but decomposition rates are even slower. So I'm going to have an accumulation. Does that make sense? And then on top of that, I've got ice for a huge chunk of the year. So even when the plants are not accumulating, there's definitely no decomposition going on because there's ice. This is one of the big issues with global warming. We have these huge patches in the high latitudes where there's lots of organic matter. Well, what's going to happen to that organic matter when the climate starts warming up? It's going to start decomposing. And if it decomposes, what is it going to be releasing? CO2. Global warming. We're just going to accelerate it even more. So question. Okay. Now let's talk about another scenario. That one was the temperature scenario. Let's talk about a water scenario. Can you guys think of another scenario where we have an accumulation of organic matter? It's totally controlled. We've talked about the temperature one. There's certainly a precipitation one. And they certainly interact with each other. Go. Underwater. Why underwater? This is a wetland. Why underwater? What's happening underwater? Anoxic conditions. The lack of oxygen. Okay. Now that's not to say that there are not organisms out there that can respire without oxygen. But oxygen happens to be the most common denominator for respiration. And if you're going to be a decomposer, you need to be able to respire. And if you don't have oxygen, you can't do decomposition. And as a result, organic matter will accumulate. Classic wetland. Organic matter grows up here where we need to have oxygen. That organic matter happens to fall into water, gets underneath the oxic zone into an anoxic or without oxygen zone. And the water basically controls precipitation. The moisture basically controls the amount of oxygen. And if I drop that oxygen content, I start having an accumulation of organic matter. Does that make sense? No, you guys are like, no, not a chance. Yeah, it does make sense if you think about it. There are organisms that can use other alternate electron acceptors for respiration, but oxygen happens to be the most dominant. Okay, most of the organisms that are alive are basically using oxygen. Okay, and if I take the system and I turn it anoxic, I basically take the majority of organisms in the world out of the picture. Which the organism, I mean, we're eating, we decompose stuff. I mean, that burger you had last night, you're decomposing it. Okay? So if I can't have oxygen, I can't have my burger because I can't respire, in essence. And it's the same thing for all these other organisms. That's not to say that decomposition is not happening in these anoxic conditions. It's just saying that the rate of decomposition is being reduced so much that the rate of accumulation is faster than the rate of decomposition, and so you get an accumulation of organic matter. Does that make sense? Okay. Next one down is clay formations. And this is when we start talking about secondary minerals, what I introduced a little bit earlier. But clay formation is most rapid at high rainfall levels. Well, why? This goes back to that chemical reaction. Water happens to be the the lingua aqua of sort of the liquid of which most chemical reactions occur. So if I have more water, I'm going to have more chemical reactions. Does that make sense? Yes? Too early. Okay, next one. Vegetation itself depends on climate. Okay, so if we're talking about biota as being one of the soil forming factors, climate has a huge impact on the vegetation. And if it has a vegetation on the impact on the vegetation, it affects the soil formation because it's affecting the biota. Right around here, this part of the country, what happens every fall? Leaves fall. We have this huge input of organic matter into the soil. Okay? Granted, it's all at the surface, but that surface material, that surface deposition, is then a food source for all different kinds of organisms that come up within and up and down and basically move that material and move it into the soil. Okay? I am modifying my soils because of leaf fall every year. Okay? Now, that's around here. Let's pick some other places. What happens if I had an environment where we were wet? We have a wetland situation. Okay? Or we have an environment that's dry, but I still have plants that are growing there, some of the creosote bushes or something like that. Okay? The nature of those plants are going to affect the amount of organic matter and the type of organic matter that moves into that soil. Those plants are then going to be the anchor for other organisms who in turn are going to affect soil processes that produce soil. Does this make sense? Okay, all being controlled by climate.
This has been a production of Cornell University, on the web at cornell.edu.